Hey everyone, welcome into the second video of the cross product virtual lecture series here. In the last video, or the first video of the series, we talked about the geometric definition of what it means to be a cross product. In this video, I'd like to talk about how to actually compute the cross product with vectors in component form. So remember, the cross product only works when our vectors live in three-dimensional space, right? So let's let u and v be vectors in v3. Then I'm going to give these component form, okay? So I'm just going to say put here, but remember the component form comes from picking up your vector and moving it so that its initial point is the origin. So here I'm going to say, all right, our vector u, give it components x1, y1, z1, and our vector v, let's say that this is the vector x2 with components x2, y2, and z2, and I want to try to compute the vector that is the cross product, right? Find the component form of the cross product. So very quickly, let's remember how the cross product works, right? So if we have our vector u, say right here, and our vector v, say right here, then the cross product of these two is the vector that is, its length is equal to the area of the parallelogram. So there's the length of the vector, and its direction is in the direction that obeys the right-hand rule. So we have u, then v. This one would be coming out of the screen the way I've drawn it here. Something like this, and maybe there's the area. So it looks something like this. So this is our u cross v. So geometrically, this is the one we're looking for, right? That's the one we're looking for. It's perpendicular to both u and v, and its length is determined by the area of the parallelogram determined by u and v. All right, well, there's some algebra that goes into this. It's actually an area of math called linear algebra that we're not going to get into, okay? But I'm going to write down the definition in a linear algebra form, which is going to require us to actually learn, define something here, all right? But let's recall, it's going to be fine, okay? We just need to know how to compute this, and then we can learn the rest of linear algebra when the time is right. But let's recall that I, j, and k, that these are the standard, what we call standard unit vectors in three-dimensional space. So remember how these work. These point in the coordinate axes directions, right? So in V3. So in other words, I is, with a hat, is the vector whose components are 1, 0, 0, points in the x direction. J is the vector whose components are 0, 1, 0, points in the y direction. And then k, of course, is the vector whose components are 0, 0, 1. It points in the z direction, 1 unit. All right? These vectors are going to be used to pick out the components of our cross product. All right? And the way that we're going to do it is we are going to take something called a formal determinant. All right? I'm going to write this as a definition, even though we already know what the cross product is. This is going to be like a second definition, a computational definition. So here's what it says, all right? So the cross product, we can give this thing a name if you want. Let's just write it in symbols, all right? U cross v, so we don't get confused. So the cross product u cross v of u with v is given by the formal determinant. Now, I haven't written this again, but I'm already assuming that we've got this component form, right? So the formal determinant, and this formal determinant is going to look like this. So again, we need to figure out what this word means, but it's going to be, it's 3x3 matrix, so I, j, k, and then the components of the next two rows are in order, the components of our vectors. So x1, y1, z1, x2, and then the components of this vector, right? So x2, y2, z2. All right? And this is great if you know what these symbols mean, which if you don't, it's not so great, right? So now I'm going to tell you exactly how this works out. So like I said, this is a formal determinant because we've got vectors in the I, J, K in the first row. So what we do is we are going to do what we call expanding. We're going to expand on these vectors. So the first thing we're going to do is we're going to think about, let me get my highlighter out here. We're going to expand on this row. All right, and what we're going to do is isolate one term at a time, and we are going to kind of ignore the rest. So we're going to do this. We're just going to look at this one term and ignore the rest of it. So there's our I. Not the rest of it. We're going to ignore the row and the column that it lives in, and we're going to really focus on the rest of it, actually. We're going to do the opposite of ignore it. We're going to focus on this lower right-hand corner here, and then we are going to kind of do what you might call like a zigzag multiplication, so we're going to go multiply this way and then multiply this way and subtract those two. So this product here is going to be y1 z2 minus y2 z1. All right, then we're going to repeat, but here's the catch. When you repeat, you have to think of this as going plus, minus, plus. So we are going to have to subtract the second component here. So we're going to do the same thing, and we're going to add quote unquote this on to what we've already got, except we're going to subtract. So this is just a rule of the determinant. So now we've got minus j, but then we're going to do the same thing, right? We're going to cross off the row that it lives in and the column it lives in, and we are going to crisscross the rest of it, right? So what's left here? Now you got to look through the red, right? So we've got x1 times z2 minus, now we're going to have x2 times z1. All right, and then finally we go to this one and we're back on plus, right? So plus the vector k, and the vector k is computed by deleting the row and column it lives in, and now the crisscross goes x1 y2 minus x2 y1. All right, and remember how the I, J, K vectors work. They just pick out components of our component vector, right? So this now is the first component of our component vector. This one we have to be careful with, though, because we have this minus sign that came out of the computation. Again, this is just part of the definition of the computation. We just have to live with this, right? But this minus has to go in, it has to get distributed, and then K is good to go, right? And so at the end of the day, here's the formula that we get for our cross product. U cross V is going to be, in its first component, it's y1 z2 minus y2 z1. The second component, the minus sign flips the order of this, actually. So this is going to be x2 z1 minus x1 z2. And then the third component is exactly this, right? So x1 y2 minus x2 y1. And so we've got two different ways to think of this now. This is, on one hand, a formula that you can memorize if you want. So you know U and V are given by x1, y1, z1, x2, y2, z2. You can just memorize this formula for the cross product if that's the if that's the preferred way for you. That's fine as long as you use it properly, right? The other option is to remember this process that we wrote out right here, right? So this definition with this thing I called the determinant. If you remember how to compute the determinant, you can just compute without memorizing the formula. So this is a chance for you to decide whether you would like to memorize a formula or memorize a process. Personally, I'm a process person. The process, I can kind of remember the general steps to it, right? And then as long as you remember enough of the general steps, you can always recreate this formula if you need to. If you're a formula memorizer and you miss a piece of it, you're never going to probably be able to go back and get the process back. But again, this is not a linear algebra course, so either one of these is fine. Now, I am going to do an example here where I show you another way to compute the determinant. So here's an example. Let's let U equal 4, 1, 2, and V equal negative 2, 2, 3. And I want to compute the cross product between these, all right? So I want to compute. By the way, remember the order really matters, right? And one of the reasons that the order definitely is going to matter when you do U cross V versus V cross U is all these minus signs. When you flip a minus sign, you have changed something, right? Subtraction is not commutative. So I'm sure you remember that U cross V is equal to minus V cross U from the last lecture. That's just the right-hand rule. When you switch the right-hand rule, you change the direction, right? You don't change anything else, just the direction. All right, so to compute this cross product down here, we're going to build the matrix. So our U cross V is going to be equal to, these vertical lines tell us to take the determinant. So you always need your I, your J, your K. Now you plug in these numbers. So it's U first. So this one goes 4, 1, 2. Those entries go in this row. And then negative 2, 2, 3. These entries go in this row. And now before I compute, I'm going to do something different. I'm going to take, just using my copy tool, I am going to take this row and I'm going to copy it and paste it right over here, outside. Another copy of it. And then I'm going to take this row, or column, these are columns, I'm going to take this column and do the same thing, right? I'm going to put this column here. And at this point, I'm going to now get out my highlighter, and here's how we're going to compute. So I'm going to take the product of the diagonals this way. I'm going to multiply these three diagonals together, all right, and add them up. And then I'm going to take the products of these three diagonals, and I'm going to subtract them off. And that's going to be it. That's going to give us our answer. All right, so I'm going to write this all out, and then as far as the color coding goes, I'll rearrange. But this is 1 times 3 times I, so that's 3I. This is negative 4 times j, so minus 4j. This is 8 times k, so plus 8k. And then we need to subtract these off. These were all the green ones, right? So these are the green ones. So these all, whoops, green. The green ones all get added. And then we need to subtract off all of the magenta ones. So I'm going to subtract like this, minus parentheses. And then these products here, it's going to be just add them up, right? So minus 2k plus 4j plus 4i, sorry, plus 12j, and this stuff all gets, like I said, subtracted off, right? And so now we just need to combine this and combine like terms, and I think that this is a little less painful than the other way. So this becomes then 3, what is it going to be? 3 minus 4i. So in the first component we have 3 minus 4, negative 1. In the j we have negative 4 minus 12. That's minus 16, right? So minus 16 in the j component. And then in the k we have 8 minus, this k should have a hat, 8 minus negative 2. So 8 plus 2, that's 10. And so there we go. There's our cross product. U cross V is negative 1, negative 16, 10. So this is this method, you just copy the columns, right? The I, the j column. You do this crisscross multiplication, and then make sure you add the ones that are going with the negative slope, which is weird, and subtract the ones that have the positive slope in terms of the lines that you've made, these diagonal lines. But otherwise, that's how you can compute the cross product when you have components of the vectors.